lecture. So I will introduce the main concepts of classification, how we assess performance of classifier classification algorithms, and also I will make a short overview of some main classification algorithms. And in the next lectures of the course, we will briefly overview some other classification algorithms in monitoring. So first of all, let's start with some main concepts. As usual, we assume that you have a labeled training dataset, which consists of input-output pairs. So xi is an input vector describing features of some object. Yi is its label. For simplicity, today we will discuss mainly binary classification. We assume that there is dependency between label value, between the label value and input vector value. And we would like to find a hypothesis which allows predicting a label value for a new feature vector, for some new object. There are many problems, applied problems that can be formulated as binary classification. For example, an object is a customer at some moment of time. As features, we can use different characteristics of this customer, like whether a customer has a job or not, what frequency and duration of calls, what already purchased services, some other characteristics. And it's obvious that if the customer doesn't use services of the company often, then with high probability the user can churn. And so, depending on the values of these features, the probability of the churn can be high. So this problem of churn prediction can be formulated as a binary classification problem. First of all, the simplest case of binary classification is so-called linear classification. We'll talk about a linear separable case. This means the following. So these red and blue dots here are our observations. So abscissa is the value of the first feature, coordinate is the value of the second feature. Each dot is an observation. There are dots, red dots are observations from the first class. From the negative class, blue dots are observations from the positive class. And the separability means that between all possible observations from the first and from the second classes, there is some linear boundary which can be defined by equation of this type. So W is a vector perpendicular to this linear hyperplane. And separability means that there is no intersection between observations from the first class and from the second class. First of all, the first question is how to estimate performance of the classification algorithm. As I said, first of all, let's consider the binary case. So the output label takes two values, -1 and +1. Classifier, which we soon I will describe algorithms for classifier construction. It can take two values, either -1 or +1, and there can be four cases. True positive, true negative, false positive, false negative. So, for example, true positive means that we predict a positive label, so the classifier outputs as 1, and this prediction is true. True negative means that the classifier outputs -1, and this prediction is true. That's it. So, from such table, on some test set, we can calculate the number of cases for which the prediction doesn't coincide with the true label, and we can estimate accuracy. So accuracy means that is actually equal to the number of cases, proportional cases, for which the classifier predicts the label correctly. In other words, the accuracy can be calculated according to this formula, where P, for example, is the total number of cases for which we get this error type, that is false positive. However, accuracy, although is a very standard metric, it doesn't take into account this class imbalance. What does it mean? Let's consider a problem. For example, for 99% of people, it's healthy, and only a small portion of the population, for example, 1% of people, has some specific illness. And if for each person, for example, for each person, based on emission data or some other physiological data, we predict whether a specific person has a specific type of illness. It's obvious that in this case, if we predict for any person that the person is healthy, in this situation, the accuracy of such stupid classifier is exactly equal to 0.99. It's obvious that this classifier doesn't have any sense. At the same time, its accuracy is 99, so formally it's quite high, almost 100%. But in this particular case, it's very important to predict accurately not the positive class, that is the person is healthy, but it's very important to predict the negative health, the negative class, that is that the person, that the particular person is unhealthy, and this class is underrepresentative in the available statistical data. So because of this, that is the class design balance, to estimate accuracy in such situation, to estimate performance of the classifier in such situation, the accuracy measure is not appropriate, and we should take into account somehow accuracy not of average classification, but accuracy specifically of how to which extent we can accurately detect the negative class that the person is unhealthy. Because if we miss some healthy person and say to that person that the person is healthy, then it can have disastrous consequences to the life of the person. So it also is very important to take into account that different types of errors can have different costs. In the example I provided, it's obvious that if we say to the unhealthy person that the person is healthy, the cost of such error is very high. Vice versa, of course, it's not also a very pleasant situation when we say to a person that the person has some illness, although it's not the case. It also can have some kind of psychological consequences, but it's obvious that the cost of such error is less than the cost of the previous error. That is why different types of errors can have different costs. And this can be taken into account when we formulate a loss function for training a classifier, and this can be taken into account when we define a performance metric of the classifier. Also, now let me also introduce several important notations. So often a classifier has the form, has the following form. So it is written on the slide. Here is it. So h of xw, this is some linear function. And actually, during this lecture, during the other lectures, I will explain how, what type of function class we consider to represent such function h, and how to fill parameters w. So h is a sample linear function. Can be a neural network, can be a linear model, can be a decision tree. W vector parameters w, these are parameters which we use during the training process. X is the input feature vector, and W0 is a threshold. So usually this linear function h, it returns a so-called score. Score, it can be different. For example, h can be a probability. In this case, we just, so if h is probability, say probability that the object with the feature vector x belongs to a positive class. Then, in this case, this value belongs to this interval, and then we just compare this value with some threshold w0, and this threshold w0 can be to some extent, so this is 0, this is 1, and w0 is somewhere here. And we say that if this value is higher than w0, that means that this value is close to 1, and that means that with high probability the object with the feature vector x belongs to the positive class and vice versa. Often w0 is set to 1 over 2, but not always. It depends on again on the class of values. In some cases, so it depends mainly on the type of the classifier we use. So in some cases, as I said, a classifier returns a value which can be interpreted as a probability. In some other cases, the classifier returns a value which can be interpreted just as some score. And in this case, so score value can take any value from a real line and just compare the score value with some threshold w0. So if the score value is higher than w0, then with high probability the object belongs to the positive class. If not, then with high probability it belongs to the negative class. And in other words, the final prediction of the classifier is either plus 1 or minus 1, depending on whether this value is higher than w0. It's obvious that